Good afternoon, everyone. I am Chanda Devnath. One of the PMRF fellows. I am pursuing my PhD from IISER Berhampur in synthetic organic chemistry. So I am the TA of this course Retrosynthesis in Organic Chemistry, instructed by Professor Shamik Nanda from IIT Kharagpur. So here in these classes I usually discuss about some concepts which may help you to solve your weekly assignments as well as to attempt some questions based on this topic. So retrosynthesis is the accumulation of lots of different type of name reactions and rearrangements, oxidation reduction, different type of reactions. So once we come to know about all these types of reactions, it is very easy for us to predict the retrosynthesis of the compound. So let's start. Till now in my previous classes I have discussed about different type of name reactions, different type of name reactions, oxidations reactions, reduction reactions and others also. If you are interested, you can go and check those classes. The videos has been uploaded and link has been shared by NPTEL also. Maybe you can go there and check. There I have discussed some previous year questions from different competitive exams like NET and GATE. So yeah, today we will also discuss about some name reactions. Before that, in the previous class I have given 2 homework for you guys to try by yourself, because in the previous classes we were discussing about mainly reduction, oxidation, and before that we have also discussed about this type of name reaction like the cyclopropionation reactions and epoxidation reactions and different. So just combining all the previous classes, I gave these 2 homework. I hope you guys have tried. For those who haven't, and just to recheck your answer, I am solving this again. So let's start today's class. After that we will discuss about some more name reaction which have not been discussed in the previous classes. So let's start. So in this reaction they have given one substrate and 2 reaction pathway A and B, and they got different product. Here they have, in this one they have one alpha beta unsaturated ketone system and alpha beta unsaturated allylic alcohol or a allylic alcohol system. This is a allylic alcohol. A allylic alcohol system and a alpha beta unsaturated ketone system. So in pathway A they have cyclopropionation has performed at this double bond, and pathway B cyclopropionation has been performed at this double bond. Between these 2 double bond, you guys can answer which one is more electron rich double bond. Obviously this one. So among these 2, which one is the more electron rich double bond? This one, because it is conjugated with the OH group. There is a allylic alcohol. There is a plus I effect by this OH group. So because of that it is electron rich, whereas this is electron deficient, because there is a conjugation with this carbonyl compound makes this double bond electron deficient. Now we know this normal cyclopropionation propionating reagent, this CH2I2Zn copper, this usually performs cyclopropionation of electron rich double bond. Electron deficient double bond usually don't participate in cyclopropionation reaction by this reagent. So to perform the cyclopropionation reaction of this part, which reagent will be preferable? This one. So obviously option, so only B, this one, because rest two we know that. So the which will be the, sorry, so obviously for reaction pathway A you need this type of reagent, because for the cyclopropionation reaction only this reagent can react for electron rich double bond. So among this, option A and B can be our right one. These are not, because we know this is which type of reagent? This is sulfonium-ylide. This generates, we have discussed about this in the previous classes. This generates sulfonium-ylide. Sulfonium-ylide usually reacts with the carbonyl compound or alpha beta unsaturated double bond or carbonyl compound. They do not react with simple double bond. They do not react with simple double bond. If they react also, that will give a epoxide. That will give a epoxide, not cyclopropane. Not a cyclopropane. So these two are eliminated. And this is also not, because this only react with the alpha beta unsaturated double bond. So this is also cut. So the correct option will be among this A and B. Now we have to choose which will be the reagent for pathway B. Now in pathway B, this alpha beta unsaturated double bond has been reacted, and in the previous classes for the sulfur ylide we have discussed that sulfonium ylide reacts with the carbonyl center, whereas the sulfoxonium ylide reacts with the double bond of a alpha beta unsaturated ketone system. So here this is generating a sulfonium ylide, because there is no oxygen, so it is sulfonium ylide, and sulfonium ylide will react with this carbonyl system, whereas the sulfoxonium ylide will react with this alpha beta unsaturated system. And here the double bond of alpha beta unsaturated ketone has been reacted. So that's why the correct option will be option B. Okay, so you can see that in a question you can't attempt a question by knowing and only one reaction. Always some questions are accumulation of two different questions, and if you know the two different type of named reactions or in different type of reaction, you can attend a single question. So let's go to the next one. In the previous class we have discussed about the reduction reactions, Barch reduction. So this is a Barch reduction reagent, you know. The previous class we have also discussed about Bayer-Villiger reaction, Bayer-Villiger oxidation. In that case we know that oxygen incorporation happens in a adjacent to the carbonyl compound, and also if there is a double bond there can be formation of epoxide, so it can generate a epoxide also. So let's go to the, in case of now OMe is a electron donating group. We have discussed in the last class, if there is an electron donating group how the reduction will happen, and if there is electron withdrawing group how the reduction will be take place. So if there is an electron donating group like OH or something, after reduction the double bond will be conjugated way. In a short, this is a method to remember like how to draw the product directly. You don't have to go to the mechanism also. If there is electron donating group, the double bond will be like this. If it is electron withdrawing group, which acid. If it is electron withdrawing group, double bond will be like this. Okay, now OM is electron donating or withdrawing? OM is the electron donating group. So how the double bond will be reduced? Now there is two groups. There is a OMe and a methyl. Both are electron donating. Both are electron donating. So we will try to place the double bond in such a way that at least both the group has some double bond in its conjugation. So let's try it. So if we see, if we look from this side, just look from this side, this double bond is conjugated with the OMe. Whereas if you look from this side, this double bond is conjugated with the methyl. So you can reduce the double in a short way, like if you want to draw the product directly, just by seeing that it is electron donating or withdrawing, this is the shortcut. If it is electron donating, the double bond should be in a conjugation with that group. If it is electron withdrawing, then double bond should be not in conjugation. So as the methyl and OMe both are electron donating, so that's why I place the double bond in such a way that it can be in a conjugate, at least each double bond is conjugated with the electron donating group. Now the next reaction is the MCPPA, and we know whenever there is a double bond and you are adding metachlorocarbenzoic acid, what happens? It performs epoxidation. But this reagent is prone to epoxide that double bond which is electronically rich. Whichever double bond is electronically rich, that double bond react faster with MCPPA. So among these two double bond, which one is electronically rich? Obviously this one, because this has only plus I effect, but this has also plus I as well as plus R effect. With plus R effect of the OMe group, it has plus R, whereas this has only plus I effect. That's why this double bond is more electronically rich. So it will react. So our correct option will be So which one is your correct option? Option C. Okay. I hope it was easy. So let's start today's session. Today we will discuss about different type of rearrangements. Pinacol, pinacolon, like pinacol, pinacolon, Fabosky, Eastern-Moser, Curtius and Beckman rearrangement. These are not enough. There are more different type of rearrangements. We will discuss those in the upcoming classes. So let's start. First is pinacol, pinacolon rearrangement. So pinacol, pinacolon rearrangement is a method for converting 1,2-diol to a carbonyl compound in organic chemistry. This is a 1,2 rearrangement, takes place under acidic condition. The name of the rearrangement reaction comes from pinacol to pinacolon. So whenever there is a 1,2 dihydroxy group, that is called pinacol. The 1,2 dihydroxy compounds are called pinacol, and after reaction the compound with the carbonyl group, this is called pinacolon. So it's transformation from pinacol to pinacolon, that's why it's called pinacol-pinacolon rearrangement. So what is the mechanism? In a 1,2-dihydroxy compound, if we add acid, it will take up this proton and get protonated, and this becomes a good leaving group and eliminates from the system. So after minus H2O, there is generation of carbocation. There is a generation of carbocation. So to make, but this is 3 degree, but to get one more stabilized carbocation, there will be performed a rearrangement. So there will be a 1,2 methyl shift. There will be a 1,2 shift. There will be a 1,2 shift. Because of that, now this carbocation is 3 degree. Sorry. So now the carbocation is 2 degree plus resonance stabilized. Initially it was just 3 degree, but now it is 2 degree as well as resonance stabilized. So this is more stable carbocation. So just to get a, what is the driving force of the reaction? So what is the driving force of the reaction? What is the driving force? Generating more stable carbocation. More stable carbocation. Okay, generating more stable carbocation. So after that, what is it then? This OH, oxygen double bond comes here, and through elimination of this, suppose to take up this proton. We get this carbonyl compound. This is called pinacolon. This is called pinacolon. Okay. So we'll discuss about this application of this question after. At last, let's go to our next rearrangement, that is Beckmann rearrangement. So what is Beckmann rearrangement? In the last class we have discussed about Baeyer-Villiger oxidation. What was that? If you remember, if we take a cyclic ketone and applied the Baeyer-Villiger oxidation, what we get? We get a cyclic ester. That is, we get a lactone. We get a lactone from a just by Baeyer-Villiger oxidation. If we are taking a cyclic ketone and we want to incorporate oxygen between this carbon-carbon bond, what we will perform? We will perform a Baeyer-Villiger oxidation. So similar to that, in case of Beckmann rearrangement, there will be an incorporation of nitrogen. There is an incorporation of nitrogen, but the mechanism is different. So this is called Beckmann rearrangement. Just to remember, just to make things easier, I am trying to compare. If you are remembering every reaction by comparing, that then it will be easy. Then just by remembering some of the reaction, you can remember all the reactions. So just try to compare, like what happening in one reaction and what is happening in another reaction. Just by comparing those, you can remember them easily. So in case of Bayer-Villiger reaction, in the last class we have discussed, in case of Bayer-Villiger reaction, what we get? If you have a cyclic ketone, if you perform Bayer-Villiger oxidation, what you will get? You will get a cyclic ester. You get a cyclic ester. That is called Bayer-Villiger oxidation. But in case of Beckmann, you will get a cyclic amide. That is called lactam. So the Beckmann rearrangement is a rearrangement of oxime functional group to substituted amide. The rearrangement has also been successfully performed on haloimine and nitrone. Cyclic oximes and haloimines yield lactam. The Beckmann rearrangement is often catalyzed by acid. However, different reagents can also be used, like tosyl chloride, thionyl chloride, phosphorus pentachloride, like the PCl5, phosphorus pentoxide, PO5, triethylamine ET3N, sodium hydroxide NaOH, trimethyl silyl iodide. So what is the mechanism? If we take a ketone and add hydroxylamine, it undergoes a water elimination reaction, so this will go here. So through water elimination, we will get this imine. We will get this imine compound. Now if we add acid or any electrophilic source, this OH gets protonated and becomes good leaving group. Then one of the group which is anti with this one. In case of Bayer-Villiger oxidation also we have learned like which group is anti to that oxygen bond that will migrate. In this case also the group which is anti to this NO bond, that group will migrate to the nitrogen and OH2 will be eliminated. Then the OH2 will attack to this carbocation center again, and through elimination of the H plus we will get this hydroxylamine type of compound, and through rearrangement through tautomerism we get this amide. Okay, so this is the mechanism of Beckmann rearrangement. Next, there is another different type of pathway the reaction can be take place, which is called Beckmann fragmentation. Suppose you are taking the same substrate, but instead of Beckmann rearrangement, it is performing a Beckmann fragmentation reaction. So what is the difference between Beckmann rearrangement and fragmentation, that we have to know. So Beckmann fragmentation is a reaction that frequently competes with the Beckmann rearrangement, and when the group alpha to the oxime is capable of stabilizing the carbocation, means this alpha to the oxime so one of this alpha to the oxime means this R or R dash, which are capable of stabilizing the carbocation, means capable of stabilizing this carbocation, which is generating here. It is capable of stabilizing carbocation. The fragmentation becomes a viable reaction pathway. The reaction generates a nitrile, that is a C triple bonded N, and a carbocation, which quickly intercepted to form a variety of product. The nitrile can also be hydrolyzed under reaction condition to give carboxylic acid. So let's talk about the reaction, then it will be easier for you. The starting is same. This OH will be with the electrophilic center and generating and becomes electrophilic. Now, instead of shifting from this carbon center to nitrogen, this bond just break. Because if there is a, so this is alpha. So if this carbocation is stable, instead of getting shifted from carbon to nitrogen center, this bond just breaks and form a carbocation center here. So it will just break and form a carbon. This is a tertiary carbocation which is stable, and then after elimination of this H, we will get this compound. Okay. So whenever there is a group or the carbocation can generated in at this alpha position can be stabilized, then instead of Beckmann reaction, Beckmann fragmentation can also be performed. We'll discuss about this topic and we'll solve some more questions. Just let's quickly cover up all this type of rearrangement, then we will discuss all different type of questions. Next is, it will be Cartier. Next is Cartier's rearrangement. So Cartier's rearrangement is the thermal decomposition of the acyl azide to isocyanate with loss of nitrogen gas. The isocyanate then undergoes an attack by variety of electrophile such as water, alcohol and amine to yield primary amine, to yield acid, primary amine, carbamate or urea derivative. So what is this? In case of Cartier acyl azide, acyl means this is acyl and this is azide. This is acyl, this group called acyl, carbonyl group is called acyl, and this 3 nitrogen is called azide. So this acyl azide undergoes a thermal decomposition and forms this isocyanate. After that, if we add alcohol, it will give ester. If we add water, we will get amine. If we add secondary amine, we will get a amide or a urea derivative. So what is the mechanism? So this undergoes a thermal decomposition. How it goes? So there is a, so this lone pair comes here and the R group shifts from the carbon center to nitrogen, just like the Bigman rearrangement. The R group shifts from carbon to nitrogen and this N2 will be eliminated and form this isocyanate. So okay, so just by whenever you are seeing some acyl azide, that will undergoes this type of thermal decomposition to form this isocyanate. After that, if you are adding any alcohol, what will happen? This will add up here. Forms this carbamate. If you add alcohol, if you add water, a similar way it will form this. After that, through decarboxylation it will form amine. If you add amide in the similar way, it will give a urea derivative. Okay, let's go to our next rearrangement. I hope everything is clear. So next is Fabosky rearrangement. I will give a short follow after just completing. I will give a overview again. Fabosky rearrangement. So the Fabosky rearrangement is a principally a rearrangement of cyclopropanone and an alpha haloketone that leads to a carboxylic acid derivative. In the case of cyclic alpha haloketones, the Fabosky rearrangement constitutes a ring contraction. This rearrangement takes place in presence of base, sometimes hydroxide, to yield a carboxylic acid, but usually ether, an alkoxide base or amine to yield ester or amide. So whenever there is a hydroxide base is used, we get an acid, but if instead of that, if we add use any alkoxide base or amine, we will get ester or amide. So let's talk about the mechanism. You can see there is an alpha haloketone, and if we perform with a base, we get a ring contraction, like from 6 member we are getting a 5 member ring with a acid group. So this is the mechanism. So you know the enolate formation reaction, we know these alpha hydrogens are acidic. The alpha hydrogen with respect to the carbonyls are acidic. In the first class we have discussed this while discussing the enolate, that alpha hydrogens are acidic. So base will take up this proton and form this enolate. After that, this O minus comes here and this enolate will undergoes an intramolecular attack to this adjacent carbon halogen containing carbon and eliminates the chlorine from the system, generating this bicyclic system. After that, if you add another molecule of OH minus, then it will attack to this carbonyl center and this ring undergoes a cleavage and forming this ring contracted 5 member ring, and we get this as our product. Okay, so mechanism is very simple. Instead of OH minus, if you add any alkoxide base like OET, then instead of just OH, here there will be a OET, that ester will form. If you add any amine, then instead of OH there will be a NH2 or in NR, so that is amide will form. Okay, so just by seeing that product, if there is a ring has been contracted, suppose with a form a 6-member ring, you are getting a 5-member ring with a ester center, then what you will think about? You will think about this Favosky rearrangement. Next, which we will discuss about, that is exchange motion fragmentation reaction. So this is quite difficult than that of the other, because there are lots of things are happening at a single reaction. So just try to understand each of the steps, because in the previous ones we are just getting the product through a simple rearrangement, but here lots of bonds are breaking and making at a single step. So let's try to solve this. It is a conversion of alpha beta epoxy ketone, alpha beta, this is alpha beta epoxy ketone, to acetylenic aldehyde. Acetylenic aldehyde means there will be aldehyde with the acetylenic aldehyde or ketone using para-toluene sulfonyl hydrazine, employing bases like pyridine, sodium bicarbonate, sodium carbonate under moderate circumstances. This reaction is generally known as exchange motion fragmentation or exchange motion Tanabe ring cleavage reaction. So let's go to the mechanism. From here you can see just what is happening. First, by adding this hydrogen, this carbonyl gets formed this hydrazone. You know, through order elimination, if you add a hydrogen to any carbonyl compound, what it will form? It will form a hydrazone. So it has formed a hydrazone. Then if you add a base, it undergoes this type of fragmentation reaction. The mechanism we will discuss now. So first is step 1. So what is happening here? In case of step 1, first this hydrogen nitrogen will attack to this carbonyl compound and open up, and through water elimination type of reaction, what you do in case of normal dehydration reaction, it will form this hydrazone. After formation of this hydrazone, what happened? This, if you add any base, here you can see you have to add any base. So if you add any base, this will take up this acidic proton which is connected to this nitrogen center and generate a negative center here. Then it will move like through this. Just see that movement of these arrows, all this happening in a single step. So this is going here, this double bond is shifting here and opening this epoxide center. After that, again this O- comes here. Through this breaking of this carbon-carbon bond, this N2 eliminates from the system. So what is the leaving group here? It's a nitrogen. This N2 eliminates from the system. Okay, and we get this acetylylic aldehyde or ketone. I just give once again, just try to get the movement of the arrows. Okay. Let's try to solve some question based on that. First, try solve this easier one. Okay, so what will happen? First, it will form this hydrazone. when you add a base, this breaks. Forming a double bond here. Now, what will happen? This O minus come here, this will break, and this eliminates from the system. This is our product. This will be our product. Sorry, this is a bond. So this will be our product. Okay, so just try to solve this one. Now first the reaction is one step backward. Now they have added a H2A2 and OH minus. We know what happens when we add H2 to OH minus to alpha beta unsaturated double bond. MCBBA performs epoxidation of electron rich double bond, and if there is electron deficient double bond, to perform this epoxidation we add H2A2. So whenever there is electron withdrawing double bond or electron deficient double bond and you add H2A2 OH minus, what happens? It will perform epoxidation of this double bond. So we will get epoxidation of this double bond. After that everything is simple. This is normal, this fragmentation. Let's try to draw the product directly without the mechanism. Let's try to draw the product directly. So what usually happens? So usually this bond breaks and there is a triple bond here. So this bond breaks and there is a carbonyl and a triple bond This will be your product. So in this way you can draw the product directly also. You can draw the product directly. You just have to break this carbon-carbon bond, and this carbon bond will be a triple bond, and this center will be a carbonyl. So this is our product. Now the same substrate has been treated with this reagent, but only one difference, that in the first one they have given H2O to OH minus, in the second one they have given MCPB, and in both the cases they will get a different product. How will you solve this? This is the interesting one. Just by changing the reagent you can get a different product from the substrate. So here you can see, we know this H2O to NaOH or H2O to OH minus perform the epoxidation of electron deficient double bond, and MCPB performs epoxidation of electron rich double bond. Now between these two double bonds, both are alpha beta unsaturated. Now between these two double bonds, which one is the electron rich, more electron rich? Obviously this one, because of this plus I effect of this methyl group. So this is more electron rich and this is more electron deficient. So whenever H2O to NaOH is there, which one get epoxidized first? Obviously the lower one. And in this case the upper one. Now if we perform this rearrangement, what we will get? Just try to draw the product directly. Just break this bond. Whereas in this case, break this bond. So have you seen the difference between this product? Here aldehyde forms, whereas here ketone forms. Okay. So just by changing the first reagent we can get two different products. Let's go to the next one. So what they have added SOCl2 to this compound. But just by seeing this one you can predict which type of rearrangement will perform here. There is a oxime group, so there will be a Beckmann rearrangement. There will be a Beckmann reaction. Now there is two possibilities. One is Beckmann rearrangement, another is Beckmann fragmentation. So which will perform here? So if you perform a Beckmann rearrangement, what you will get? You get a lactam with a 7-member ring and nitrogen incorporation. We know 7-member rings are not that much stable. 7-member rings are not that much stable. But if we undergo the Beckmann fragmentation, we can get a carbocation at this place. This is alpha. Wow. This is alpha to this. So you can get a carbocation at this level, at this step, at this position, and this carbocation is stabilized by this OH. So you can perform the fragmentation here. So just try to draw both the product and then decide. That will be better, I think. So if we perform a fragmentation, what you will get? We'll get this as our product. 7-member rings are not that much stable, whereas if we undergo a fragment, instead of fragmentation, instead of rearrangement, if you undergo a fragmentation type of reaction, what you will get? If just these bonds break at this position, what you will get? And this okay. Let's go to the next question. So I've understood the which will then in these two cases which will form. Obviously this fragmented one, this will not form because 7-member, it has been seen in the reaction vessel that this is not formed because 7-member rings are not that much stable, whereas we get a Breakman fragmentation product, not a Breakman rearrangement product. So we will get a Breakman fragmentation product. You have understood like what is the difference between Breakman fragmentation and rearrangement? So just by seeing the nature of the substrate, we have to predict which will undergo a Breakman fragmentation or Breakman rearrangement. This is another one. So you have to determine which will be the intermediate formed and the major product in this course of this reaction. Options are given. So first what will happen? Acyl chloride. this bond breaks. There is no such form of lactam, so obviously this will undergo the Beckmann fragmentation. You can see just by seeing the option you can predict that is Beckmann fragmentation or rearrangement, because there is no formation of lactam or a amide. So obviously there will be a bond cleavage. There is a carbocation, so the intermediate will be carbocation, so between 1 and 2. So intermediate is carbocation, not carbonitrile, so only a carbocation. As it is a tertiary carbocation, so what can happen? There is a H available here. So what will be the product? Option 1. Okay, understood? So it will undergo the Beckmann fragmentation. What will happen here? So they are given a dust. This is basically a fluoride source. This is a silicon fluoride salt kind of system. Silicon can give a electrophile type of nature, and the fluoride can act as a anion. I don't remember the full form, but if you just search, let me give you 1 second. I will just. This is diethyl ammonium sulfur trifluoride. It is diethyl ammonium sulfur trifluoride. Diethyl ammonium sulfur trifluoride. So what happened in this case? This is similar type of Beckmann type of substrate. So what will happen here? Beckmann rearrangement or Beckmann fragmentation? Whenever there is a alpha stabilizing group, so you can see there is a 3-degree carbocation can be formed here. So obviously it will go through and if you go through a Beckmann rearrangement, there will be a 7-member ring. But if you undergo the Beckmann fragmentation, there can be formation of carbocation at this 3-degree position. So it will undergo the Beckmann fragmentation reaction. So we try to draw the product directly. There will be a formation of carbocation. With the CN. Now, as this is a fluoride source, this fluoride can attack here, giving this as our product. Okay, there is another question. So here I have already drawn the So if you have this type of substrate and it undergoes a Beckmann fragmentation reaction, what will happen? So there is a sulfur at this adjacent position. So this sulfur can attack to this alpha position and undergoes a fragmentation. So it will give this now. As nitrogen has lone pair, so it can attack again at this position and sulfur opens. Forming is agitating type of system which are stable. Okay, understood? This is a complex version. Now we know about this. So now just you have to design the retrosynthesis of this one. Just try to design the retrosynthesis of this one. This is the last question of today's session. So we have to design the retrosynthesis of this product. Based on whatever we learned today, we have to predict the retrosynthesis of this one. So let's start. First, we know about Beckmann rearrangement. We know about Beckmann rearrangement. So from that one, you can predict that it can be formed from this carbonyl compound. Okay, this is just an incorporation of nitrogen. So if this one is performed through a Beckmann rearrangement, it will give this one. So it will further. If you want to cleave this one, what will get? We get a phenol and normal Fidelkraft alkylation or acylation. We'll get this product. Okay, so this is the retrosynthesis of this compound from simple phenol and acyl chloride. Instead of acyl chloride also you can add Ec2O, acetic anhydride. That can also be possible. Okay, so this much for today's class. So I just give an overview. So first we solved some homework which I gave in the last class. Then after that we started discovering some rearrangement reaction. First we started with pinocol rearrangement, then Beckmann rearrangement, Beckmann fragmentation, Cartier's rearrangement, Favosky rearrangement, then at last Eastern motion fragmentation. Then we solved different type of questions based on that, and how just looking at the substrate nature we can predict which will get from Beckmann fragmentation or Beckmann rearrangement. And just by changing the epoxidation reagent we can perform epoxidation of the different double bonds. Then we solve some questions and we predict the retrosynthesis of this product. So just by knowing these reactions you can design retrosynthesis of a complex molecule. Okay, so thank you for today's class. We'll meet in the next class next Sunday, same. So there I will discuss some more reactions, name reactions or different type of rearrangement, fragmentation and all. Thank you everyone. Have a nice day.